Alright, so this is nuclear chemistry part 2. We're going to talk about nuclear reactions, okay? Kind of how they work and some of the applications that can be used. So first thing first is we're going to have to write a balanced nuclear equation showing mass number and atomic numbers for radioactive decay. Remember, they're trying to stabilize themselves, so it's what we call radioactive decay. When a radioactive material lets off something in order to become stable, it's decaying. All right, so the process called radioactive decay describes how a nucleus spontaneously breaks down emitting radiation. And we've talked about the forms of radiation as well in alpha, beta, and gamma terms, okay? So radioactive nucleus, a nucleus plus radiation, all right? And most common one we can think of is uranium. All right, so in a nuclear equation, you have the radioactive nucleus that will equal the nucleus, the new nucleus, plus the radiation. The sum of the mass numbers on each side of the equation must all be the same. So if I let off something like 2 mass units, that means the other side has to somewhere find those 2 mass units. So both sides have to equal. The sum of the atomic numbers on each side of the equation must be the same. So alpha decay, easiest one. Remember, we can hold a piece of paper and in front of us and block it, and if you're more than 4 inches away, or 4 centimeters away, you're fine. Like you got no worries. Okay. I think I did. Now that I think about it, I think the last lecture I was wrong on my length. Anyway, it doesn't matter. You have to be very, very close. Describes a radioactive nucleus decrease in mass number by 4 and a decrease in its atomic number by 2. Well, why does that make sense? The atomic number is directly related to the number of protons, okay? And the mass number is related to the number of protons and neutrons. And then if we know alpha particles have the same nucleus makeup as helium, 2 protons, 2 neutrons, we know that the mass number would have to decrease by 4. So, and this is demonstrating just what I was saying, okay? So the radioactive uranium nucleus, okay, lets off the radiation as an alpha particle. And then, here, handy dandy pen, right? So radioactive nucleus, uranium nucleus, radiation comes off in the form of an alpha particle, and then the new nucleus looks like thorium-234, all right? Well, how does that work? Well, look at our original mass number, 238, and look at our original atomic number, 92. Well, now the nucleus has a mass of 234, well, subtract 4, 238, that makes sense, and we lost 2 protons, so the atomic number is going to drop down by 2. So if we have our radioactive nucleus here, 238, 292 uranium, we come over here, we've got our new nucleus, that looks like thorium, and then we have the alpha particle that comes off. And remember, this needs to equal back to the uranium-238. Okay, well, 234 plus 4, 238, and 90 plus 2, 92. All right, all interrelated. So, how do we complete a nuclear equation? So, first thing we would have to do is write the incomplete nuclear equation because, well, you got to start somewhere, right? Then we have to determine the missing mass number. And based on the missing mass number, we can determine the missing atomic number, and then we determine the symbol of the new nucleus, completing the nuclear equation. Now, you definitely need your periodic table for this. Remember, the periodic table in chemistry is the ultimate cheat sheet. It'll tell you pretty much anything you want to know. Well, within reason. All right. So write an equation for the alpha decay of Rn-222. Okay. So, write an incomplete nuclear equation. All right, well, we've got Rn. We know that an alpha particle is going to come off. All right. So, if we go 222, Well, we know that the new atomic mass number, because we're going to lose 4, is going to be 218. Then we have to determine the missing atomic number. All right, well, 82 minus 2 is 84. So if we use the periodic table and we look for the atomic number 84, it is polonium. Okay, and then we know that 222 minus 4 is 218. Cool. And we know that polonium is atomic number is 84. So our new nucleus looks like polonium 218, and our alpha particle has completely left. Beta decay, a neutron in the nucleus breaks down into a proton and an electron. The number of protons increase by 1, okay? The number of neutrons decrease by 1. So if we increase by 1, decrease by 1, guess what? It's going to remain the same. An electron is emitted, which is what we call our beta particle, the electron, from the nucleus. The atomic number increases by 1, which is correct because the protons are going up by 1, but the atomic mass number will remain the same because it is a net zero change. All right, so this is a radioactive carbon nucleus, okay? Beta particle comes flying off, and then we have a new stable nucleus, all right? So if we look at this, since we gained a proton, the atomic number goes up by 1, and it looks like nitrogen now, okay? So here is our start. Here's our radioactive radiation taking place. Beta particle comes off. New atomic number, same atomic mass, okay? So let's look at the beta decay for potassium-42, all right? So we got 42, okay, and that's our atomic mass. And we know in a beta particle, the mass isn't going to change, so we know that the mass is going to be still 42. So we know that we're going to gain a proton, which is going to increase the atomic number, right? So we got to figure out, okay, well, what plus, okay, well, we're saying what minus 1 will equal 19? Well, we bring it over, we add 1 to 19, that's 20. So our new nucleus is going to look like, we start with potassium-42, okay? Our nucleus becomes calcium-42, simply because of that atomic number change, and our beta particle comes flying off. Now, positron, in a positron emission, okay, a proton is converted to a neutron, and a positron is emitted. The mass number of the new nucleus is the same, but the atomic number will decrease by 1 because a proton is converted to a neutron. Remember, our atomic number is directly related to the number of protons, but the mass will stay the same. All right, so it says write a nuclear equation for the positron emission of rubidium-82. All right, so here we go. All right, our net mass yield is going to be 0 because we lose a proton, but we gain a neutron. All right, so 82 minus 0 is 82. Cool. But we also know that we are going to lose that proton, meaning that the atomic number is going to go down by 1. So if that atomic number is going down by 1, it was originally 37, now it becomes 36. So our new equation, okay, we have to look for the atomic number 36, all right? It'll go from rubidium-82 to Kr-82 plus the release of the positron, okay? So our mass stays the same, but our atomic number decreases. In gamma radiation, energy is emitted from an unstable nucleus indicated by the symbol M in the following, the mass number. The mass number and the atomic number of the new nucleus are the same. They don't change, okay? They're exactly the same. But the M indicates that it is letting off gamma radiation, all right? So radiation sources, we have an alpha emitter, okay? Radiation goes off, we have a new element. Beta emitter, radiation comes off, plus a new element. Positron emitter, radiation comes off, new element. Gamma emitter, radiation comes on, off. Same element, but it's a stable nucleus of that element. So that brings us to radioactive isotopes, or transmutation. Radioactive isotopes are produced in a process called transmutation. It's when a stable nucleus is made radioactive by bombarding it with small, high-speed particles, such as alpha particles, protons, neutrons, and small nuclei. Okay, so bombarding particles. So we're taking our particles and we are slamming them in to a nucleus. Okay, like this is stable right now, but we are going to force our way in with these, in this case, alpha particles. All right, and then that yields a new radioactive nucleus, such as nitrogen-13 plus this neutron. All right. So, what radioactive isotope is produced when neutron bombardment bombards cobalt-59 and the alpha particles emitted? All right. So, how do we do this? All right, we got cobalt, we got this neutron coming in. What do you guys think? Well, what's going to happen? The particle has a mass of 1, right? So our mass is going to increase by 1, all right? But we also have an alpha particle coming off. So what's going to happen? It will then decrease by 4. So if we say 59 plus 1, well, net 60. But then because we have an alpha particle coming off, we're going to drop down 4. So that is how we'll deal with the atomic mass. Now determining the missing atomic number. All right, we look over here. We gain nothing with the atomic number. But over here, we have an atomic number of 2. So what we need to do is subtract 2 from the atomic mass of cobalt. So giving us this new atomic number of 25. So we go back to our periodic table. We take our information, and we are left with manganese, so 56, all right? So this would be the complete equation. I hope that made sense. I know it's some new information, but it's basically how these radioactive formulas work.